A deer runs in front of a semi-truck driving 90 feet per second. The driver immediately slams on his brakes to avoid hitting the deer. The velocity of the semi is recorded in 2-second intervals according to the graph below. The brakes are applied at time t equals 0. The deer was 400 feet in front of the driver. Did the semi hit the deer? So we're going to look at this question today, and we're going to answer it with a Riemann sum. So first thing we're going to do is look at the data that was provided here in the form of velocity at different times. So over here we're going to have a table with time and velocity, and over here we're going to have a chart plotting those points. So our first point is going to be at time 0, velocity 9. So what this means is that when the driver sees the deer and reacts, he's going 90 feet per second for velocity. That is going to be reflected over here in this first point at time t equals 0 and velocity of 90. Next point is at time t equals 2 and velocity of 78. So we can go ahead and plot that over here. Next point is time of 4, velocity of 50. So we can expand that point. And finally, our last point here, at time t equals 6, the semi has come to a stop. So his velocity is 0. So what we're trying to find here is the total distance that the semi drove before coming to a complete stop, and then we can tell if that was 400 feet or less or greater to know if he hit the deer or not. So basically what we're trying to do is find the area under a sort of a curve that you could imagine going through these points, because that would be sort of his continuous velocity. The semi's velocity is going to decrease from 90 feet per second up here down to 0 per second in a continuous manner, but we only have these certain data points. So rather than sort of finding an area under this curve, we can just find an area under some rectangles. So for example, if we were to look right here, the area would actually represent 20 feet per second times 2 seconds, which would actually give us 40 feet. So this area here would represent 40 feet. And so basically we're trying to figure out how much area is under this whole curve. And we can get an initial estimate to that by finding an area starting here with our leftmost endpoint and making that into a rectangle over this interval from 0 to 2 seconds. And this is going to start us off towards finding our left endpoint estimate, which for short we'll just call that LEP. So the area of this first rectangle here is just going to be the height of it, which is 90, represented by our velocity over here, times the width of the rectangle, which is 2 seconds, represented by our 2 here, which we can call this distance in general. We'll just call that delta t for the time difference. And we multiply these two together, and we end up with 180 feet per second. Now if we want to look at our next interval here between 2 and 4 seconds, we still have the same delta t here. It's still going to be 2 seconds. And taking that rectangle, we multiply the height of it, 78, times the delta t, which is 2, and we get 156 feet for the area of that second rectangle. And for this last interval here, again, that delta t is still 2, and we're going to multiply it by the height of the rectangle to get 100 feet for our last rectangle. So if we add all of these distances up, we'll get our left endpoint estimate, which we're going to denote as L3 because it's a left endpoint estimate with 3 rectangles, and that is just going to equal the addition of all 3 of these areas. So 180 plus 156 plus 100, which is going to give us an estimate of 436 feet for our left endpoint estimate. And if you imagine these rectangles here that we showed, they're actually going to be bigger than we would expect a continuous curve of velocity to look like. So this left endpoint is actually going to be an overestimate. But having found an overestimate with our left endpoints, if we actually find the right endpoint estimate, that's going to give us an underestimate, and we'll kind of box in the possible distances that the semi might have traveled. So let's go ahead and do that next. So for the first interval here of our right endpoint estimate, we're going to go ahead and, instead of using the side on the left like we did before, we're going to use the height on the right of this interval. This height here, recall, was 78. So we're going to call this our right endpoint estimate, And we'll go ahead and just call that REP for short. And of course that first one is just going to be 78 times 2, which is going to give us our 156. And for our next interval here, between 2 and 4, again we're going to use the right endpoint that we have here, which in this case is 50. So we got 50 times 2, which we found earlier, is equal to 100 for the area of this other rectangle. And finally our last rectangle is going to have a height of 0. So we're going to have 0 times 2 as the area, which of course is just going to be 0. So adding up all these areas, we end up with our right endpoint estimate, which we're going to denote as R3 because we're adding up 3 rectangles. And that, of course, is just going to be equal to 156 plus 100 plus 0, which gives us a total of 256 feet. And if we look at our plot again, you would imagine that if we had a continuous curve, it's going to be decreasing gradually through this, and that curve is actually going to be larger, and that area under that curve is going to be larger than the green area that we just estimated. So our R3 is going to be an underestimate. So having found our left endpoint estimate, which is an overestimate, and our right endpoint estimate, which is an underestimate, we can actually find a more accurate one by averaging the two. So let's go ahead and move on to our trapezoidal estimate. For our trapezoidal estimate, we would connect the points like this. Notice we're no longer using rectangles to find the area, but we add up trapezoids instead. While this is a bit more complicated, you can imagine the benefit of this is that it would line up better to the continuous velocity we would expect between our points. So we could calculate this area separately using some geometry to get the triangles, but there's really no need to because our trapezoidal estimate is just going to be the average of our left and right endpoint estimates. So we'll call that our T3 estimate for trapezoidal, and we'll just go ahead and find that by adding up L3 and R3 and dividing that by 2. L3 estimate here, and our R3 estimate here. And our midpoint estimate becomes 436 plus 256 divided by 2, which equals 346 feet. So finally we got enough information at least to take a stab at an answer here. So for our answer here, what we could say is that our T3 and R3 indicate the semi did not hit the deer because both of them are less than 400 feet. However, our L3 indicates that we went 436 feet, which is beyond that 400 feet where the deer was. So our L3 tells us that our data allows the room for the potential that the semi did actually hit the deer. So our overall answer is that we are uncertain. So probably not the definitive answer we were looking for here, but the data doesn't really allow us to go much further than that. I can say with certainty, however, that no animals were harmed in the making of this video.